Alright, let's talk about differentiability. So f is differentiable at 0. Well, no, at a. Since f is differentiable at a, let's write out what that means. There exists some linear map from Rn to Rm which satisfies the limit as h goes to 0 of f of a plus h minus f of a minus lambda of h, all divided by the norm of h, is going to equal 0. Now again, here this is sort of lazy notation. What if you want to be really specific in your writing, you would keep in mind that h is a vector and not a real number. So you would really need to write either h as a vector approaches the 0 vector, or the norm of h approaches the number 0. Both of these things that I've written down here are equivalent to saying that h is a vector which approaches the 0 vector. But I'll just sort of keep in mind that we assume h to be a vector, and I'll just write limit as h goes to 0, even though it can be deceptive if you don't know what I'm referring to beforehand. Okay, so what does this mean? Well, if the limit as h approaches 0 of this fraction equals 0, then certainly if we look at the limit of the top thing, then this must be 0, because otherwise there'd be no way that the fraction would possibly have a limit equal to 0. Okay? Now we're going to do a string of... Here. Well, first, let's say, since lambda is linear, there exists some m such that for every vector h, the size of lambda h is less than or equal to m times the norm of h. This is using problem 1-1. Alright, so then how do we use this to our advantage? Then, okay, so we have 0 is the limit as h goes to 0, and again as a vector of f of a plus h minus f of a minus lambda h. And now we can use the reverse triangle inequality to say that this is greater than or equal to the limit of the norm of f of a plus h minus f of a minus the norm of lambda of h. And again, I believe we proved this reverse triangle inequality in a previous exercise. And by the way, what I've done here is I've technically, I guess, done 2 steps here. What's actually true is that if you erase this limit here and you erase this limit here, then this inequality, the remaining inequality, holds. This holds. But this holds for every single h, and so when you take the limit as h goes to 0 on both sides of the inequality, it still holds. Okay, so we have this. And again, we're taking the limit as h goes to 0 of the difference of these two things. And let's see. So what we can do is we can write this as the limit as h goes to 0 of f of a plus h minus f of a minus the limit as h goes to 0 of lambda of h. And again, this is because of this, or because this limit is technically being taken on the entire difference. Now, I guess there's a little subtlety going on here between the fact that we've broken the limit up between two things, because typically the rules are if you have two things whose limit exists, then taking the limit of the sums is the same as taking the sum of the limits. That doesn't necessarily hold when you have two things whose limits does not exist. You can have two things where the limits do not exist, but the limit of the sum exists. Say you take limit as h goes to 0 of h minus h. This limit is going to be 0, but the limit as h goes to 0... Wait, no. limit as h goes to infinity of h minus h. So for every single h, this difference is 0, so the limit of the difference exists, but the limit of each thing individually is infinity and thus does not exist. So there is a little bit of subtlety, but the fact that this limit exists, or the fact that this limit exists and equals 0, and that we can use it to bound this limit, and the fact that this limit, which we will prove, the fact that this limit exists means that everything is going to be fine. This is something I remember struggling a lot with when I was going through baby rooting, is that things typically work nicely if you've got something, you're taking the limit of two things and there's one thing where you're not quite sure if the limit exists, but there's another thing where you know the limit exists. But anyways, so we have this thing. Now, remember, we have lambda of h is less than or equal to m times the norm of h. But this is for positive things. If we put minus signs, then the norm of lambda h is going to be greater than or equal to negative m of h. And this inequality here remains if we take the limit as h goes to 0. And so, therefore, this is greater than or equal to the limit as h goes to 0 of f of a plus h minus f of a. And now we subtract the limit as h goes to 0 of m of h. But of course, this limit over here, this limit is just 0. And so this is equal to the limit as h goes to 0 of f of a plus h minus f of a. Okay, so we know that this limit here is less than or equal to 0. But it's an absolute value, or it's a limit of positive numbers, so whatever the limit is, it has to be greater than or equal to 0. So, thus, limit as h goes to 0 of f of a plus h minus f of a, this limit must be precisely 0. Alright, so this limit equals 0. And that's basically everything that's basically it. That's all you need for continuity at A. So, alright, well, if we went to, I guess we could take the time to sort of put this in a format that's similar to the definition, the epsilon-delta definition of continuity. So let's go through and do the work for that. So, okay, so if this limit exists, for all epsilon, there exists a delta. If, let's see here, if the norm of h is less than delta, then the norm of f of a plus h minus f of a is less than epsilon. Alright, so given epsilon, or using the same epsilon and delta, if the distance from x to a is less than delta, then we can write x equals a plus h, where the size of h is less than delta. And this you can just see from, like, you could draw a picture. You've got a here, and this radius is delta, and x is within delta of a, then there's this segment between a and x, which you could call h, and the length of this segment h must be less than delta, because otherwise x could not possibly be within a delta ball of a. Okay, so we've got, so if x minus a is less than delta, then we can write a And so then the difference between f of x minus f of a is going to be f of a plus h minus f of a. And since h is chosen to have norm less than delta, this difference must be less than epsilon. And so, yeah, that's the delta epsilon phrasing of the continuity condition. And so we've proven that f is continuous at a, and we've completed the proof.